You here, so gas power cycles, we will have, like I said, will actually have both closed cycles and open cycles. While closed cycles are primarily referring to internal combustion engine, and we have two types here. One is what we call the Otto cycle, the other one is what we call the diesel cycle. While open cycles, we also have two types, Brayton cycle and jet propulsion cycle. For you, this semester, this will be the focus. We will not be going into open cycles. Of course, I asked you guys to write an article for the assignment for this gas power cycle, so you probably would have studied the other one if you have chosen that topic. But for mechatronic students, you won't actually study about the open cycles, but for the mechanical students, next year you will be studying this. Okay, so just as overview here, for this chapter, we will evaluate the performance of gas power cycles, for which the working fluid remains a gas throughout the entire cycle. So like I said, gas power cycles, everything is gas. Then we will develop a simplified assumption. So for gas power cycles, we usually will require some form of assumptions. We will also talk about this. Then we will see how a reciprocating engines work, which is internal combustion engine. Then we will see the two power cycles, which are Otto cycle as well as diesel cycle. Okay, let's look at the initial case here first. So here we will dump a bit more things that serves to confuse you in a way. Okay, so when we are running a cycle, how should I say this? So I need to give you another extra term to put in between. So in second law, which is in the previous chapter, we learned that we have reversible cycle as well as non-reversible cycle, right? Then we said, so Carnot cycle is the reversible cycle. And we mentioned that then that time, the way that we think about it is Carnot cycle will be the ideal version. Then the non-reversible one will be the actual version, which actually is not exactly the case. Okay, so now, so Carnot cycle will be the cycle with the best efficiency, but usually what happens is that we actually cannot reproduce Carnot cycle. Okay, so we need to modify the Carnot cycle so that it becomes a cycle that we can use. But then when you modify the Carnot cycle so that it becomes an actual cycle, one cycle that we can use, most of the time, let's say we look at the PV diagram here, the actual cycle will actually look something like the green cycle, which is something that's very hard for you to analyze because everything is not constant, like there's a lot of variables there. So in those forms, so we will still idealize this kind of cycle to a certain level, meaning we still make some assumptions so that it is easier for us to analyze, but those are still not the reversible or Carnot cycle. So here we will have one more, which is the ideal cycle. So you can see here that we will actually have, so Carnot cycle is the totally reversible cycle with the highest thermal efficiency, while we have another cycle that we call the ideal cycle. So the ideal cycle is an internally reversible cycle, so it is only reversible internally. We don't care about the environment, and it is actually the simplification of the actual cycle. So the flow goes this way. Carnot cycle will have the highest efficiency. The ideal cycle then will be somewhere between the Carnot cycle and the actual cycle. So it goes something like this. It probably won't make so much sense in this case yet. When it comes to when we look at the actual one of the meaning Otto cycle, then you will probably see lah. So reversible cycles such as Carnot cycle have the highest thermal efficiency, operating between the same temperature level. So whenever you talk about Carnot cycle, always remember that the keyword is that it always has to be between the same temperature levels, because the moment you change the temperature, efficiency will change. Okay, so yeah, so what we are doing is basically the blue text over here. The analysis of many complex processes can be reduced to a manageable level by utilizing some idealization. So the ideal cycles are only internally reversible, but unlike the Carnot cycle, they are not necessarily externally reversible. So therefore, the thermal efficiency of an ideal cycle in general is less than that of a totally reversible cycle. So we just talk about that. Operating between the same temperature limits. So what you are doing, again, this is not a very good analogy if you look at the photo figure over there, but it is something like that. So let's say when you are running a simulation, for example, you want to see how much heat you need in order to heat up a potato, but then you do not know the properties of the potato. So then you try to model it as a water, and then you see how much heat is required to heat up the water to the same temperature. Of course, water to potato in a way is a bit hard to put them in the equal term now. Maybe the better way would be something like if the potato has a very irregular shape, for example, then you try to model it as a, let's say, a round potato, a proper one. So you will see that the heat required probably would not be the same also, because the surface area is not the same, but it's close enough, like something like that. Okay, so thermal efficiency equation. So we came back to this equation. So this equation is important when we are analyzing power cycle, because we use it to determine how efficient the cycle is in converting heat to work. So the idealization and simplification in the analysis of power cycles. So the cycle does not involve any friction. So these are the idealization that we do. So therefore, the working fluid does not experience any pressure drop as it flows in pipes or devices. So one thing that is important when we are considering cycles, both of these cycles, actually all the cycles when we are analyzing, is that we will never consider any drop in pressure during pipe flow in our case. Okay, so if the pressure is meant to drop or rise, let's say when it passes through a compressor or turbine, then that's fine. But if it is not supposed to drop, then we don't consider those drop, meaning we don't consider those friction. So all expansion and compression processes take place in a quasi-equilibrium manner, enhanced reversible, and the pipe connecting the various components of a system are well insulated, so we don't lose heat during the pipe flow itself. Okay, so then you can see here on both PV and TS diagram, the area enclosed by the process curve represents the network of the cycle. So even though we mentioned before, PV diagram is network, TS diagram is net heat transfer, right? But in a cycle, they are the same thing, because we are assuming all the energy that goes in equals to all the energy that comes out. So the net change in heat is the net change in work. Okay, so here we also kind of talk about this, but here we are talking about a Carnot cycle for an open system. So you can see that here we have 4 open systems in the diagram, but this is still a closed cycle. This is still a closed cycle, correct? Like as we mentioned just now, because the working fluid will be recirculating inside infinitely. Okay, but then open system, closed system doesn't really make much difference, because you can see that the 4 processes here are the same thing: isothermal heat addition, isentropic expansion, isothermal heat rejection, isentropic compression. For closed system, back then we talk about that in terms of compression and expansion. But then you can see that the PV diagram and TS diagram are the same. And now that I talk about this, I realize this slide most probably shouldn't be here, because we are not going to use the open system version. But anyway, it will be useful for the reverse refrigeration cycle later on. But yeah. Okay, so again, we are just talking just a short revision on Carnot cycle, but this time we are looking at the open system version, that's all. So here we show you the derivation of the efficiency of the Carnot cycle, but actually you have learned this in a way, right? Because so here thermal efficiency equation can also be equals to 1 minus Q out over Q in. And how do we get this? Because we say that work net equals to Q in minus Q out. And then here we show you a more proper way how we get the temperature ratio thing. So here we know that Q in is actually TH because we are setting this. So you can see that for Carnot cycle, TS diagram is just a simple rectangle or square. So meaning we are assuming isothermal process. So from here you can see Q in is actually just TH S2 minus S1. Q out is TL S3 minus S4. So then which is also S2 minus S1 based on this diagram here. Because we are assuming, again back here, we are assuming isothermal and isentropic process. So constant temperature, constant entropy. And this is actually how we get the temperature ratio thing. So 1 minus CL over TH. So again, this is only applicable when for Carnot cycle lah, because only in Carnot cycle you get the graph to looks like this, in this shape. Okay, so now we will have an overview of what we call the reciprocating engines. Okay, so reciprocating engine is another name that we use for internal, what we call internal combustion engine. Essentially, this thing over here. Some of you, if you're interested in car, you have seen this kind of thing, right? It is actually how your car engine works. And so if you have a look at this, reciprocating engine essentially is a piston cylinder device. What you learned in. So which means that reciprocating engine is a closed system. At least after some assumption. In actual, it cannot be a fully closed system, or else you can't inject fuel in, right? Because you need to send fuel in. So in a way, it is not a fully closed system, but when we analyze it, we look at it as a closed system. Again, we will see it later. Okay, so there's a wide range of applications for reciprocating engine. We use them for automobiles, trucks, like aircraft or ships. So a very basic structure of it is as you see on the slides here. Okay, it's a piston cylinder device, but this piston cylinder device do have an intake and an output lah. So here we have an intake valve, exhaust valve, and then we have what we call the bore, which is the diameter. We have the stroke, which is the distance the piston will move. Okay, so we look at this in more detail in the next slide. Okay, so the piston, which is connected to a crankshaft, so this thing will be connected to something here. There is a, and then that thing will just keep turning. So that's what we call a crankshaft. It will just keep turning, and then it will just push and pull the piston. But that's not our focus lah. For now, we just want to see the top part. So the piston will reciprocates. That's why we call it a reciprocating engine, because it will just keep moving up and down between two fixed positions. So these two positions are the what we call the top dead center as well as the bottom dead center. So TDC and BDC, essentially the maximum distance and the minimum distance that it will move between. So this distance itself is what we call the stroke. So the distance between these two positions will be what we call a stroke. So it is the largest distance the piston can travel in one direction. So one direction will be half revolution. So one revolution will be when it moves down and up one time. That will be one revolution. That will be when the crankshaft turns one round. So the bore is the diameter of the piston. And as you saw just now, we have what we call the intake valve as well as the exhaust valve. So intake valve is where, when it opens, we will supply what we call the air-fuel mixture into the piston. So air-fuel mixture, so mixture of air and fuel, this is for combustion purpose. Exhaust valve is when after the combustion, we don't want all this exhaust, it will open, then we need to expel them out to the environment, and that's where your car is expelling all the exhaust. Okay, so in this diagram, you can see what we call a spark plug or a fuel injector here. These two are for, the purpose of these two are for the combustion, essentially, to ignite the air-fuel mixture. Then, the reciprocating motion of the piston is converted to a rotary motion by a crank mechanism. So we talk about this. Okay, so more terms here. So clearance volume is the minimum volume formed in the cylinder when piston is at TDC. So when your piston is all the way at the top, usually you will not compress fully because you will still have air and the fuel inside, right? So this distance here, this volume here is what we call the clearance volume. When it goes all the way down, so all the way this entire thing, this will be the maximum volume. So volume formed when in the cylinder when piston is at PDC. Displacement volume, actually there's no real meaning to this. It's just volume displaced by the piston and it's moved between TDC and BDC. So any position, depending on what is the position of the piston, that volume is the displacement volume. So it can be any value. So here we also have what we call the compression ratio. So since this whole thing is very dependent on the change in the volume, as you can see here, the compression ratio is the ratio of the maximum volume over the minimum volume. That is the compression ratio. So what are the volumes that the engine is working between? And their ratio will be the compression ratio. Okay, one more term. Mean effective pressure. So in a lot of the cases, for some reason, we actually will measure the performance of an engine based on pressure. So this mean, or essentially it is because when you are calculating, let's say if you want to calculate the power produced by an engine, a lot of things are constant. The only thing that is not constant that you can measure is actually pressure. So we will actually measure this pressure based on the other constant, and then actually you just multiply, you will get the power. So pressure itself is actually the main thing that you can measure. So mean effective pressure will be the theoretical constant pressure, or just the constant pressure. Theoretical one is actually called indicated mean effective pressure. It's the constant pressure that if it acted on the piston during the power stroke, would produce the same amount of network as actually developed in one actual cycle. So this is actually the pressure when you want to, the pressure that is equivalent to the work produced by the engine itself. So this MEP, or mean effective pressure, is basically just the work net over the total volume. So the work net that you can produce over the total volume. So MEP is a parameter that compares the performance of reciprocating engines of equal size. So like I said, if you want to find the network, actually all the other things are constant. Just the pressure is not a constant. So like let's say if you're comparing engine of same size, then this pressure itself will be the deciding factor on how much better it will perform, or basically the performance. Okay, so for reciprocating engine or internal combustion engine, we have two different types of engine. One is what we call the spark ignition engine, which is the gasoline engine. The other one is what we call the compression ignition engine, which is also what we call the diesel engine. So what are the differences between them? The main difference would be, one we are using gasoline, the other one we use diesel. So the one that our car is using would be the spark ignition engine. Okay, so in this case, so for this one, you can see that all the differentiating parameters between them. So one is that their basic cycles will be different, and based on the name, obviously type of fuel is different. The way we inject fuel is also different. Ignition process that are different is different. Their efficiency will not be the same. The speed will not be the same. Basically, almost everything are not the same. Okay, so for now, you can ignore the picture first. Okay, we talk a little bit about them first. So the spark ignition engine or the gasoline engine. For this engine, we will burn the air fuel mixture by igniting them with a spark plug. You can imagine it like, how many of you are still using gas stove at home in your kitchen? Yeah, so when you ignite your gas stove, you turn the thing, then there's a plug sound, right? That's actually the spark plug. Basically, you cause a spark for the fuel to burn. So this is actually how this type of engine works, a simplified version. So it is more advantageous to use spark ignition engine for application up to 285 kilowatt because they are relatively light and lower in cost, and is particularly suitable for automobiles. So your car, this is what we use. The compression ignition engine works slightly differently. Instead of using the spark plug, we actually don't put in what we call the air fuel mixture. For a compression ignition engine, you supply air into the engine first, and then you compress the air. So you compress the air until it is at a very high pressure. High pressure meaning it will be at a very high temperature as well. But of course, air by itself, no matter how high temperature, it cannot burn. So when it reaches the temperature or the pressure that we want, then only we inject diesel in. So when you inject diesel in, then because the temperature is very high and diesel is very volatile, it will just burn. And that's what we call and which is also why just now here we show that it's either a spark plug or a fuel injector. So spark plug will be the one for spark ignition engine. Fuel injector is for diesel engine or compression ignition engine. So normally this is preferred for application when fuel economy and relatively large amount of power is required. So if you need a large amount required, then we will use this kind of engine, which is also why diesel we use it for for trucks and stuff, bus also. Alright, so here probably it's not very clear how they work, and so I will show you a video here to see how a representation of how these two engines are different and how they work.
Internal combustion engine. Gasoline and diesel engines are the two most commonly used internal combustion engines. Even though their operations seem similar, they have some interesting differences, and each has advantages over the other. This video is aimed at exploring these differences and advantages from a scientific point of view. Both engines have the basic four strokes: intake, compression, power, and exhaust. There are differences between the two engines due to the difference between the way fuels burn. Gasoline readily evaporates, so it gets mixed with the air efficiently. As a result, just a spark is sufficient to produce smooth combustion in a well pre-mixed gasoline engine. On the other hand, diesel does not properly mix with air. However, if atomized diesel is sprayed into high temperature air, spontaneous combustion will occur. This means that in gasoline engines, the fuel and air should be pre-mixed. While in diesel engines, mixing happens only during the combustion. This is why diesel engines use a fuel injector, while gasoline engines use a spark plug. You might have noticed that gasoline engines are less noisy and vibrate less compared to diesel engines. This is because the combustion process in a premixed mixture is smooth and propagates well. But in a diesel engine, the combustion could begin anywhere in the combustion chamber, and it turns out to be an uncontrolled process. For this reason, to reduce the excessive vibration and noise problem, diesel engines require a more rugged structural design than gasoline engines. This is why gasoline engines are always preferable for lightweight applications. Since the diesel engine is compressing only the air, it can achieve a good compression ratio without risk of self-ignition. But in a premixed gasoline engine, such a high compression ratio is not possible. The higher the compression ratio, the better the efficiency of the cycle. This is the reason why diesel engines have better fuel economy as compared to gasoline engines. An interesting question many people wonder is, what if I put gasoline into a diesel engine or vice versa? Diesel in a gasoline engine will not even cause firing. The reason is simple. Diesel is less volatile and will not mix with the air properly, and the sparking will not initiate any combustion. On the other hand, if you put gasoline in a diesel engine, you are spraying a highly volatile fuel into a chamber of highly compressed and hot air. This will lead to detonations rather than smooth combustion. Eventually, the engine components will get damaged. So that's a big no for gasoline in a diesel engine. Thank you for watching the video.
Okay, sorry, just now I said something wrongly. Gasoline is the volatile one, not diesel. Okay, so here it shows you all four processes of basically for both of the engines, so compression ignition engine as well as the spark ignition engine. So for this engine, so here what you see here is that they will take 4 different strokes for the whole cycle to happen. So one is what we call the intake stroke, then after the compression stroke, power stroke, and exhaust. You call it exhaust stroke. Yeah. So you can see that for both engine, for both diesel engine as well as gasoline engine, they actually will go through the same 4 processes. Just that during the combustion process, they are slightly different. So here you can see that since what you see here, since they require 4 strokes for one cycle to happen, we also call this the 4-stroke engine. Okay, so now, so there are actually 2 different types of engine as well: 4-stroke or cycle, 4-stroke cycle as well as 2-stroke cycle. So what you saw just now was what we call the 4-stroke cycle, which is a more common one, where it takes 4 strokes or 2 revolutions in order for one cycle to happen. But there's actually a simpler variation, which is the 2-stroke cycle. This one you only need 2 strokes, 1 revolution for one entire cycle to happen. So the 2-stroke engines are generally less efficient than their 4-stroke counterparts, but they are relatively simple and inexpensive, and they have high power to weight and power to volume ratio. So because they're lighter, and because they produce power more frequently, because every revolution will produce power, then they are slightly stronger. So for this chapter, our main focus is still on 4-stroke cycle. 2-stroke cycle is not your focus here, but I will show you one video to just letting you see what are their differences. So you remember this Otto cycle and diesel cycles are actually independent of this 4-stroke and 2-stroke cycle. So meaning again, each of them can be 4-stroke or 2-stroke cycle. So just a quick video lah, just to show you how it looks, how they works. This one.
You probably have some knowledge of how internal combustion engines work. They involve pistons, cams, explosions, etc. But do you know the difference between two-stroke and four-stroke engines? Throughout the history of automotive design, there have existed two main types of gasoline-powered combustion engines: the two-cycle, or two-stroke, and the four-cycle, or four-stroke engine. As you may have guessed, the names of each engine suggest exactly how they operate. For an engine to complete combustion, there needs to be combustion of the air-gas mixture and expulsion through the exhaust port. The way this process is repeated varies between each engine type. A two-cycle engine completes a combustion and exhaust cycle in only 2 strokes of the piston, whereas a four-cycle engine takes 4 strokes of the piston, thus their names. For a four-cycle engine, there's a power stroke where the piston is down, which is caused by combustion of the fuel mixture. Then there's an exhaust stroke where the piston is up, which pushes the gas up and out of the engine. The following 2 strokes include an intake where the piston is down to draw in the fuel, and a compression stroke where the piston is up to start the process all over again. Examining this process closer yields the observation that the whole cycle is powered by the initial combustion stroke. This means that the combustion of the fuel mixture needs to impart enough power on the piston to allow it to rotate the crankshaft twice. A two-cycle engine, on the other hand, has much simpler mechanics, as it basically consolidates the different processes of a four-stroke engine. There is a power stroke, which also releases the exhaust after a certain amount of travel, then an intake and compression stroke that draws in new fuel and completes combustion. These are the basic mechanics of each engine type, but both have significant advantages and disadvantages, which has ultimately led to a more widespread use of the four-stroke engine. Looking first at efficiency, a four-stroke engine achieves great efficiency due to the fact that nearly no fuel is wasted in the intake cycle. In other words, the fuel is drawn into a closed system. In a two-stroke engine, since the fuel is drawn in during a combined intake and compression stroke, the mechanics needed for this also means that some fuel can escape while being drawn into the cylinder, thus decreasing efficiency. Modern two-strokes use fuel injection, which increases their efficiency to levels close to four-strokes, but generally, a four-stroke can be much more efficient. Efficiency isn't everything, though. A four-stroke is certainly more efficient, but they also weigh upwards of 50% more than a comparable two-stroke engine. This weight is due to more complexity within the motor's mechanism, which also leads to significantly more moving parts in a four-cycle engine. In terms of simpleness and easiness to fix, a two-stroke engine easily wins out. The last main difference between these engine types is how oil is added to the engine. In a two-stroke engine, the oil is typically mixed with the fuel, usually somewhere in a 50-to-1 to 20-to-1 range. This makes oil application fairly reliable, but it also means increased fuel costs and fuel modification when you buy it. A four-cycle engine uses normal gasoline like your car, which also happens to be a four-stroke engine, and the oil is injected from a separate reservoir. This eases the burden of fueling the engine up, but of course there's always the possibility that the fuel pump will break. All things considered, even with the drawbacks of the four-cycle engines maintain higher efficiency over two-strokes and can produce more power than comparable two-stroke engines. There have been cars made with two-stroke engines, but they mostly died off in the early 1980s due to efficiency constraints. Modern two-stroke engines are still produced for small watercraft and gardening equipment. Sometimes simple design, like the two-stroke engine, doesn't always beat out more complex mechanics. Thanks for watching. If you enjoyed this video, you can watch more of our videos here and here.
Okay, so you can see that essentially they're quite similar. It's just that for two-stroke engine, we consolidate the design so that two different processes can happen at one single stroke. Then you complete one full cycle with one revolution. Okay, so mainly like the video said, these days we just use two-stroke engine or two-stroke cycle mainly for like small equipments because they are light and then they can produce power based on a high power to weight ratio. Okay, I think now I will give you 5-10 minutes break. Then after that we will then look more into detail how we analyze these cycles. now that you have understand how the cycle works, or at least I hope you can understand from the video.
这个各差这样就是它。